Okay, everyone, we're into lecture 7.2, so this is the second part of Unit 7. Again, we're filling in some details on the multiple regression topic. Today, we will look at the mechanics of hypothesis testing, of testing linear restrictions. And the underlying concept isn't too difficult, just a bit of matrix algebra, or not matrix, sorry, linear algebra. We'll do matrix algebra later. Just a bit of linear algebra. And then I'm going to switch over to my R Studio screen so that I can show you exactly how it works in R. I'll show you the function that you can use in R for testing linear restrictions, and I'll also show you, by working through the mechanics the long way, I'll show you what it is that R is doing, and then that'll hopefully relate it to what you scribbled out on pen and paper. And so let's get started. Grab your pen or your pencil and your paper, and here we go. So we're going to look at section 4.4.1 in the textbook. And our topic today is F tests of linear restrictions. And this is a section of the textbook that I find is a bit brief compared to what all we have to actually figure out. So I will go through the material step by step on paper, and then I'm going to switch over to an R Studio screen, and I'll show you how it all works out in programming. So we are looking at what are called linear restrictions, and we have a multiple regression model. So let's write it out like this: alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus the error term. Now, you're familiar with the idea of a t-test. We could use a t-test to test the null hypothesis, for instance, that beta 2 equals 0. All right, so you know how to do that one. And then you've also seen the idea of the F test, the regression F test, which is the null hypothesis that beta 1 equals 0, and beta 2 equals 0, and beta 3 equals 0, and beta 4 equals 0, that they all equal 0. Which can also be written beta 1 equals beta 2, beta 3 equals beta 4, and they all equal 0. And it can also be written R squared equals 0. Because, as we talked about a while ago, if your model consists just of a regression on a constant, and you've got no explanatory variables, just the constant, the R squared always equals 0 from that. What we're going to do, though, is look at what are some intermediate tests. So this is basically testing one coefficient, and this is testing all the coefficients. But what about if we want to test, say, beta 3 equals beta 4 equals 0? Well, it would not be correct to just look at the two t-statistics, because neither of those t-statistics is actually testing the combined hypothesis here. And it wouldn't be correct to look at the f-statistic because it's not testing this hypothesis either. Or we could think of an even more complicated one. Suppose we want to test, what if beta 2 equals beta 3, but we don't necessarily need them to equal 0. We just want to see if beta 2 equals beta 3. Then we clearly can't use either the t-test or the f-test. So these are examples of what are called linear restrictions. Any hypothesis that can be written as a linear function of the betas is a linear restriction. And so we're going to come up with a new procedure. So it will involve the following. It'll be estimate the original model, and we call the original model the unrestricted model. And we're going to obtain the sum of the squared residuals from that model. So we obtain from that the sum of the squared residuals, and we're going to call these the sum of the squared residuals with a subscript u, meaning unrestricted. The unrestricted sum of the squared residuals. Okay, so you know that when you run a regression, one of the things that you get the residuals, and then you can get the sum of the squared residuals, and so that's SSR. And in the original model case, that's the unrestricted model. We get the unrestricted sum of squared residuals. Then we rewrite the model with the restriction imposed. And then we estimate the restricted model, and we obtain the sum of the squared residuals from the restricted model. And we call that SSR, and we'll put an R subscript on it. So that means this is the restricted sum of the squared residuals. So we, this part here, we rewrite the model with the restriction imposed. That's where the textbook kind of skips over it really quickly. And I want to spend a bit of time showing you how you do that. And then we now have two sum of squared residual numbers. And what we want to do is test if the sum of the squared residuals changes by much. So if you impose the restriction and the sum of the squared residuals changes, the first thing you should think about is it going to get larger or is it going to get smaller? Okay, now in the unrestricted case, we're using all the explanatory variables that we have, and we are minimizing the sum of the squared residuals when we run a regression. That's what you do. That's what ordinary least squares does. So we're going to get the smallest possible sum of squared residuals. Once you impose a restriction, you are either taking variables out of your model, or you are limiting the way the coefficients can vary. So you can't improve the fit of the model. All you're going to do is detract from the fit of the model. So that means the sum of the squared residuals goes up when you impose restrictions. So it's always going to be the case that the sum of the squared residuals in the restricted case will be greater than or equal to the unrestricted sum of the squared residuals. And what we want to do is see if this difference is large or not, if it's going to be a big change or not. So what we're really checking is the sum of the squared residuals in the restricted case minus the sum of the squared residuals in the unrestricted case. Is that a big number or not? And so that's going to be the basis of our test statistic, whether this becomes a big number or not. And to convert it into a test statistic where we will know how it's distributed, and this part I'm just telling you, you don't need to worry about how this is derived, but the formula is going to look like this. So if we use this formula, so we take the sum of the squared residuals in the restricted case minus sum of the squared residuals in the unrestricted case, so we take that difference, and then we divide by Q, where Q equals the number of restrictions. And then we put all of that over the sum of the squared residuals in the unrestricted case divided by the degrees of freedom in the unrestricted model. So you can think of this, so again, we're looking at this term here, the sum of the squared residuals minus sum of squared residuals. So how much that changes per restriction that we impose. And then we divide that by the sum of the squared residuals in the unrestricted case over this degrees of freedom term. It turns out that that follows an F distribution, and it has, since the F distribution has two parameters, two degrees of freedom parameters, the degrees of freedom are Q and N minus K minus 1. So the idea then will be, if this fraction turns out to be a large number, then that means we're way up in the tails of the F distribution, so we would reject the null hypothesis. So it follows the F distribution under the null hypothesis that SSRR equals SSRU. So if these don't change, if the sum of the squared residuals doesn't change, that will be 0. And under that null hypothesis, this follows an F distribution. And so if we end up with a very large value, then that would mean this is probably not true. And so we would reject the null hypothesis in that case. So if we go to the chapter section, so this is how we write the hypothesis that's being tested when we're looking at the regression F statistic, the test on whether R squared equals 0. And in that case, the F statistic, we've seen the formula before. It's R squared over 1 minus R squared, and then N minus K minus 1 over K. And that follows an F distribution. To have a more general form of F tests, then we start with writing an unrestricted model. So in this case, we've got 3 explanatory variables. And then an example of an F test or a restriction that we want to test with an F statistic would be, in this case, beta 1 equals beta 2. To test that, we need to come up with the restricted version of the model. Well, if you impose those, then what you end up with is a regression just with beta 3 and x3 in it. And so that's the restricted model, where you only have x3 left as an explanatory variable. And the form of the F test is, as you can see, the sum of the squared residuals in the restricted model minus the sum of the squared residuals in the unrestricted model divided by sum of the squared residuals in the unrestricted model, and then you've got the additional terms q and n minus k minus 1. And then there's one little additional possible version of the F statistic, which we're not going to bother with. What he's pointing out here is that instead of computing the sum of the squared residuals, you could compute the R squareds of these two regressions. However, this one doesn't always work. So we won't bother with that one because this one does always work. Okay. And I'll switch to a blue pen here. Let's go with our first example. We want to test the null hypothesis that beta 1 equals beta 2 equals 0. So we have the original model, and I'm going to always refer to that as the original model, just a linear regression with 4 variables. That yields the sum of the squared residuals in the unrestricted case. In the textbook, he puts the subscript UR, and I find that just makes it a little confusing between restricted and unrestricted, so I just call it U. Then we impose the restriction. So what does that give us? If we impose the restriction, then our regression model is now y equals alpha plus, okay, beta 1's gone, beta 2's gone, so then we have beta 3 x3 plus beta 4 x4 plus the error term. So now you run this regression. So you run that regression, and that yields the new sum of the squared residuals. And that's SSR subscript R for the restricted model. Now, how many restrictions are we testing? We're testing 2 restrictions. So we're testing 2 restrictions here. Even though I've written it in a single line, it's beta 1 equals 0 and beta 2 equals 0. So 2 restrictions. And suppose, well, let's just say n minus k minus 1 equals 40, and the original sum of the squared residuals, the unrestricted case, is 1000, and the sum of the squared residuals in the restricted case is 1200. And as I mentioned, it has to go up, it can't go down. So then the F statistic will be 1200 minus 1000 over 2. And on the bottom we have 1000 over 40. Okay, and that equals 4. That's what I have in my notes. Let me just double check. That's 200 over 2, so that is 2, that's 100, and 1000 over 40 is 25, so that's 4. Okay, so this is distributed F with, what have we got, 2 and 40 degrees of freedom. Okay, so we want to see then if this exceeds the critical value for the 5% level of this distribution. So does f equals 4 exceed the 5% critical value for f to 40? All right. Well, let's have a look. So we go to the back of the textbook here. Table 1, table 2, table 3, that's chi-squared. Yep, here's the S tables. Got to turn it this way. So we have the numerator degrees of freedom along here, and we got the denominator degrees of freedom down here. And this table is the 5% critical values. If we want the 1% critical values, they're in the next table. So we want the critical value for numerator degrees of freedom is 2, and denominator degrees of freedom is 40, and that is 3.23. So so the 5% critical value equals 3.23, and so f is greater than 3.23, so that means we reject the null hypothesis that beta 2 equals beta 3 equals 0 at 5%. Okay, so that's how the procedure works. Now, when we go to do it in R, we'll get R to look up the numbers in the table for us. You won't have to use the book, but let's try a different example. So let's try our second example. This time we're going to test the null hypothesis that beta 1 plus beta 2 equals 0. Now, why would we have a restriction like that? Well, there can be various reasons, but if, for instance, let's say you were estimating a production function, a Cobb-Douglas production function, and you wanted to test if you have constant returns to scale, then you'd be testing, do the coefficients add up to 1? So in this case, it would be beta 1 plus beta 2 equals 1 if you only had two factors in your production function. However, in this case, we're going to test beta 1 plus beta 2 equals 0. Now, this can be rewritten beta 1 equals minus beta 2. So we're just bringing that over to the other side. So we, as before, you obtain the unrestricted sum of squared residuals. We already did that. Then you impose the restriction. And watch how we do this. So we have our regression model alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus the error term. Now beta 1 equals minus beta 2. So let's do this. Alpha plus minus beta 2 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus epsilon. So you saw what I did there. And now we've got two beta 2's in here. So we're going to collect terms. So we have alpha plus beta 2, and when I collect terms, I have the x2, and then I have minus 1 times x1, so it'll be minus x1. So that's taken care of both those terms, and then I have beta 3 x3 plus beta 4 x4 plus epsilon. And now, since I'm thinking about how I'm going to do this on the computer, what I have is beta 2 z plus beta 3 x3 plus beta 4 x4. Z, nothing to do with z scores there. I just needed another letter, another variable name, where z equals x2 minus x1. So if you think about what you're doing in R, you're going to have a line where you generate a new variable. And the new variable will be x2 minus x1. And then you plug that in instead of x1 and x2 in the original model. So the code would look something like this. The unrestricted model, we would have, so we'll call it M1 equals linear model y on x1 plus x2 plus x3 plus x4. And to get the sum of the squared residuals, so what's that going to be? Sum of M1 $sign residuals squared. All right. And then we'll have to do our second model, restricted. We'll do this. Z equals, what did we say, x2 minus x1. Now our second model is going to be LM y on z plus x3 plus x4. And now the sum of the squared residuals from the restricted model will be the sum of the residuals squared. Take the sum of that. So now we've got SSR U, SSR R, and then as long as you can calculate your degrees of freedom, the F stat will be SSR R minus SSR U over, and what have we got here? We have one restriction, and then we divide by SSR unrestricted over, and then I think we're using 40 still. So then that would give us the F statistic that we want. I will show you more examples in our studio itself. The main thing you need to follow here is when I say impose the restriction on the regression, that means plug it in to that linear equation, and that's going for you to do that, it's going to require that you define a new variable. Okay, here's another example. Let's say we want to test the null that beta 1 minus beta 3 equals 0, which can also be written beta 1 equals beta 3, and beta 2 plus beta 4 equals 1, which can also be written beta 2 equals 1 minus beta 4. So we're going to test these two restrictions. So I'm going to skip the first part where you get the unrestricted sum of squared residuals because you've already seen that. So now we impose the restrictions. So start by writing out the unrestricted model. Alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus the error term. Now we substitute in our restrictions. So we have alpha plus beta 1, but that equals beta 3, plus, and we have beta 2, but that equals 1 minus beta 4 x2 plus beta 3 x3 plus beta 4 x4 plus epsilon. And then we just need to collect some terms. So we have alpha plus, we've got a couple of beta 3 terms here, beta 3 x1 plus x3. And when you're writing these out, sometimes it's handy so that you remember what terms you've collected. Put a little check mark underneath. So we've used that, and we've used that, and we've used that. Okay, and then we have plus x2, and we have minus beta 4 x2 plus beta 4 x4 plus epsilon. So now we collect terms again. We have beta 3 x1 plus x3 as before. We've got this x2 sitting by itself. I'll have to figure out what to do with that one. But we've got beta 4, and then we're going to collect these terms, and it looks like this, x4 minus x2 plus epsilon. Now this guy doesn't have a coefficient on it. So what are we going to do? Well, we're going to bring it over here to the left-hand side. So then we have y minus x2 equals alpha plus beta 3. And I'm going to substitute in a variable name here. So let me call that one W plus beta 4, and just need to pick any old variable here. I'll call that G. Plus epsilon, where W equals x1 plus x3, and G is x4 minus x2. All right, and from there you obtain the new sum of the squared residuals, and it all goes on from there the same way. So the key step here is knowing how to impose those restrictions. And the way you impose the restrictions, you just express the hypotheses in this form. So one of the coefficients equals an expression of the other coefficients. So in this case, beta 1 equals beta 3, beta 2 equals 1 minus beta 4. And don't forget, in this case, you would use Q equals 2 and construct the F statistic using Q equals 2 and the other things that we just calculated. So we construct the F statistic and then carry on as in the previous example. All right, I have one more example I want to show you, and that is, suppose we test beta 1 equals beta 2 equals beta 3 equals beta 4 equals 0. So in this case, Q equals 4, but it's also going to be the case that Q equals K, because the way we count variables in the model, in this case, k equals the number of slope coefficients or explanatory variables. I'm going through this example because you should recognize that this is the Regression F test. So this is what the Regression F statistic tests. So the restricted model is y equals alpha plus error term. So regressing y on a constant, we know what that gives us. That gives us an r squared of 0. And the reason the r squared equals 0 is that the sum of the squared residuals in this case equals the total sum of squares. So we saw that weeks back, that if you regress the dependent variable on a constant with no explanatory variables, you get an r squared of 0 because the sum of the squared residuals equals the total sum of squares. So the F statistic is, in every case, it is the sum of the squared residuals of the restricted model minus the sum of the squared residuals in the unrestricted model over Q divided by the sum of the squared residuals in the unrestricted model over n minus k minus 1. All right, so sum of the squared residuals in the restricted case, well, we already said that equals the total sum of squares because we're regressing on a constant. And this is the sum of the squared residuals in the unrestricted case. Okay, and then we divide by Q. And we have the sum of the squared residuals in the unrestricted case, and we divide by n minus k minus 1. And now what I'm going to do is divide the top by the total sum of squares and divide the bottom by the total sum of squares. And then that gives me 1 minus the sum of the squared residuals. Now, it's the unrestricted sum of squared residuals, but if I leave off that u subscript, then that's referring to this original sum of squared residuals. So I'm just going to do that. I'm going to call it sum of the squared residuals divided by the total sum of squares, referring to the original model. And that's over Q. And then we've got the sum of squared residuals over the total sum of squares over n minus k minus 1. And now I'm going to multiply the top and the bottom by n minus k minus 1. So then I get 1 minus sum of squared residuals, 1 minus SSR over TSS times degrees of freedom over Q. And that's all over. It's going to be this on its own. And it's going to be handy for the next step to add and subtract 1 on the bottom, which I'm allowed to do. Right. Now, what you might have noticed as we're going through this is the formula for r squared. Okay, so we have r squared times n minus k minus 1 over Q, and I have 1 minus, now this expression 1 minus 1 plus sum of squared residuals over TSS. If I put a bracket in there, that's 1 minus sum of squared residuals over TSS. Okay, so then that is, now what I'm going to do is multiply the top and the bottom by Q, but in this case, Q equals K. Corresponds to the number of explanatory variables. So I've got R squared times N minus K minus 1 over, well, that's R squared there, the term in the brackets, so this is over 1 minus R squared. And I've got a Q on the bottom, but it's K this time. So then I get that formula. And of course, we've seen that before. That is our formula for the F statistic in the multiple regression case. Just find where we are here. So that's our F statistic. So that's why the F statistic takes that form. And I went through this so that you don't think there's a different formula every time for the F statistic. In fact, that's the formula for the F statistic. It just happens to be the case that if you test that all the slope coefficients equal 0, that formula turns into that. So we learned that one first, but that's actually a special case of the general formula for the F statistic. The general formula for the F statistic when you're testing restrictions is the change in the sum of the squared residuals over Q divided by the unrestricted sum of squared residuals divided by degrees of freedom in the unrestricted model. And the special case, if you're testing all the slope coefficients equal 0, then you get that form that we learned earlier on. So those are the steps. Now what I'm going to do is switch over to my R screen, and I'll just walk you through an example using one of the class data sets. All right, so here is a familiar site for you. It's the RStudio window. Now, you'll notice I've been working on this for a while. I've got a whole bunch of stuff in the console, and sometimes it's nice just to get rid of all of that so that you can have a clean screen to work on. So if you do Control L, you can just clear out the console and get a new start. So I'm going to use this data set, the educ.csv data set, and that's one with the list of countries and then education spending, GDP, and population. And here's the code we're going to work through. And you'll notice that I've written it with spaces and comments so that I can go away from it, come back to it, and find my way around in it again. So first thing I'm going to do is clear the memory, read in the data. Now for this one, I also need to read in a package, the car package. Nothing to do with cars, that's companion to applied regression. And so in the R tutorial in section 7, you'll have seen the instructions for how to download and install a package. While I'm here, I'll just, so you can do that using the method in the manual. It also turns out in RStudio, there's a way you can do it just on this tab here with packages. If you want to install a package, you just click install, and then you get a box there. You type in the package that you want to install. So in this case, I wanted the package car, but I won't install it now because it's already installed. It's right there. And But in order to tell R that you're going to use that new package, you need to use this command library and then the name of the package in brackets. So we'll implement the car package, and I'm going to clear out the memory. So now you can see the environment is emptied. And then I'm going to set the command to not use scientific notation. And then I'm going to read in my data file, and there we go. We've got everything in there. And in this case, the variable names are in the header. Everything is simple that way. So I'll just use an attach command to generate my variables. And when you see this list of statements here, it's in red and it looks like they're error messages, but they're not error messages. It's just telling you that it's R's kind of obscure way of saying that it's bumped all of these things directly up into the top level directory, and you don't need to use the attach command. Right, so hold on, I'm just checking that as I'm recording this, that my microphone is working. It seems to be working. Yep, the microphone is working. I would hate to get through a whole recording of this and go back and discover that the microphone wasn't working, and I have to redo the whole thing. All right, this next command here, I do that just because GDP, the numbers are so different than the other numbers. We get these tiny little regression coefficients, 0.00000 whatever. And so it's just easier to rescale the data sometimes so that the regression coefficients will come out a little closer to each other. Here we have some commands just to get the summary statistics, and I'm using the print in order to dump it into the console. You'll notice I don't have a sync command set. That's because I want you to be able to see what happens. So I want it to go to the console. If I used a sync command, that would send it all to a file over here in the files list, but I don't want to do that. So if I run these statements, then we get the summary. So the country variable, 38 observations, and it's character data. The education numbers, the mean is 44.99, and then we got the minimum, the maximum, and the quartiles, and the median, and then summary stats for the GDP and population. And then I do the this cat statement to get some correlations. You'll notice those are statements that you used in your first assignment. And then I'm going to add a couple of extra regression variables, GDP squared and population squared. So I'll just run those. And now I have my basic regression model, and I'm going to, this will be my unrestricted. So it'll be the one that has everything in it. GDP, population, GDP squared, and population squared. So by adding in the squares, that means I'm not just looking for a linear relationship between GDP and education, or population and education spending, but it could be, say, an inverted U-shape relationship, or it could be convex upward. So I'll run these, and here you see the data suggests that education spending goes up as GDP goes up, and that's not surprising. But the GDP squared coefficient is negative, so it's going to be a negative quadratic relationship. In other words, an upside down U shape. And so we could, if we wanted, figure out where the upside down U shape has a peak. We won't do that, but that's something that we could do. And then education spending goes down with population. That's unusual, but bear in mind that's after we control for the effect of GDP. And then in this case, population squared is insignificant. The t statistic is small. Probability value is greater than 0.05. And then our F statistic, well, the F statistic is 257. It's huge, so the p-value is 0, basically. Okay, so now let's do a linear hypothesis test. And what we want to do is test if these quadratic terms are both 0. And there's a way of using the package, but I'll start by doing it the long way that I just showed you in the lecture. So we have the unrestricted residuals, so we pull those out of the regression, like so. And then we get the sum of the squared residuals, and that's SSR with the subscript U. And so let me just run those. And then we have to run the restricted version of the regression. So in that case, the restricted version is just the linear terms without the quadratic terms. So I'm just taking GDP2 and POP2 out. So we run that. Then we get the residuals from that, take the sum of the squared residuals, and that gives us SSR subscript R. And now I need N and K and Q. All right, so actually I guess I could get rid of that space there. So N, K, and Q, calculate those. And then I'm going to calculate my F test. And so this is the formula. We have SSR restricted minus SSR unrestricted, divide by Q, the number of the tests, and I have 2 tests here. And then divide all that by the unrestricted sum of squared residuals, divided by N minus K minus 1. So that's the formula for the F test. And so I'll calculate that, and then I'm going to print it out with a cat statement. And I can get R to calculate the p-value. And you'll, in the section, I think it's in section 8 in the RStudio manual, how to calculate a tail probability. So the syntax here is I want R to calculate the p-value for an F distribution. The value that I want it to use, that's how far out on the tail, is the F test. And it has Q and N minus K minus 1 degrees of freedom. The way that term is calculated, that will give me the area under the distribution up to that point. But I want the area under the distribution past that point, so I take 1 minus that amount. And so that gives me my F statistic, and the F test is 3.8709 and has a p-value of 0.0309. So it's less than 0.05. So we reject the null hypothesis that both of those are insignificant. Now, in R, if you have loaded the package car, companion to applied regression, one of the commands that's in that package is linear hypothesis. And it lets you write a linear hypothesis. And the way you write the linear hypothesis is you have to use that C array, and you're going to write the hypothesis in words. So you have it in quotation marks. And in this case, I want to test that the coefficient on GDP2 equals 0 and the coefficient on POP2 equals 0. So I have those 2 expressions, and I have them in quotes, and then I put them in the array using the C function. So, and then I'm applying this restriction to the unrestricted model. So that is the object that I created when I ran the original regression. So I run that command, linear hypothesis. I assign the output to test 1. And if all goes well, when I print this, I get the F statistic, 3.8709, and my p-value is 0.03089. So R is doing these steps for you. And so that's the easy way to do this. So let's do one more. I'm going to test, in this case, if the GDP effect equals a population effect. In other words, back here, if in this regression, if the coefficient on GDP equals the coefficient on population. And to do that, well, I could run a restricted version of the regression. And what I would do is define a new variable. So I call it W, and my new variable would be W equals GDP minus population. And then I would run this regression 2 equals W. So if I applied the restriction that GDP equals population, I'd run that, and then I would get the new sum of squared residuals, and then I construct my F test, and I print it out. Don't have to do all that. I just have to enter a single linear restriction, and I'm still putting it in the C function, but my restriction now is GDP equals population, and I'm applying that to my unrestricted model. And let's see what we get. We get an F statistic, a very large F statistic, 26.948, and a very small p-value, so we can reject that null hypothesis as well. Okay, so that's how you do the linear restrictions in R. You can do it the long way, if you like, or you can let R do the work for you, and all you have to do then is learn how to use that linear hypothesis command. And the instructions are in the R tutorial for you. So that's it for Unit 7, and next week we are on to Unit 8.